part 1. 1 second. Right. Yeah. So first, as usual, we'll start with some basic terminology. Yeah. So the first definition is probably a known definition already, but still I'll just define it. So we have semigroup homomorphism from S to T, so we know what that is. What I want to define is the kernel, because this will be useful for us to parameterize the Green's relations of functions. So the kernel of a map is basically, it's a relation on the set. So it's an equivalence relation. It's a partition of the domain set, which basically x and y are related if phi x and phi y go to the same point. So basically the fibers of the map phi. Now, this definition is obviously just, so it's not a new definition. Like, this is the generalization of the definition that's there in groups. So whenever we have inverse elements available to us, then we just define kernel as a set of points that go to the identity, if we have the identity. And then when you take the translates, the cosets of those points that go to the identity, you get the cosets give exactly the same partition as this definition of kernel is giving us. So this is just a generalization, so not anything completely new, just an adjustment that we have to make. Okay. Yeah, so as I already mentioned, it will be useful for us in describing the Green's relations of semigroups of functions and sub-semigroups of them and so on. So we know what a congruence is, but there is this special kind of congruence, which is just basically quotienting a semigroup by an ideal. So we can start with an ideal. Okay. So we know what an ideal is. Ideal is this, when we say ideal, we mean two-sided ideal. And we take the quotient of S with this congruence. So we take I cross I, and we have to add elements of the form S comma S, because to make it an equivalence relation. And then we can quotient it. Okay, we can quotient S by this congruence, and we just call it as mod I. Okay, right. That's what we are doing. Okay, now kernels are also a congruence. Okay? Kernels are also a congruent, because if x and y, I mean, if x and y go to the same point, means if x is related to y by the kernel, then tx and ty also will go to the same point. And so kernels are a congruence. Okay? But kernels are more general than the congruence created by ideals. Okay, so in ideals, I mean, if x and y are related, then u, x, v, and y and x all will be related. But that doesn't have to imply. So there is a mistake here. So here I meant to say. So here I meant to say it does not imply. Okay, yeah. So by this I mean to say that not all congruences or not all kernels. Not all kernels come from ideals. Okay, yeah. Right. So, right. So that's what I wanted to say. Yeah, but this doesn't happen in other places. That's why I'm making the distinction, because in groups and rings, every ideal leads to a kernel and so on. So, but here this is not the same thing. Okay. So here ideals are special cases and kernels are more general. Right. So then we come to the main algebraic objects that we have, that is simple semigroups. A simple semigroup, as one can expect, is just a semigroup which has no proper ideals. Okay, so there is no I which is contained in S. Okay, so it is sort of like it's indecomposable. Like you cannot quotient it with any ideal. Okay, they are like minimal objects, and that's why they are useful. Right. But there is a difference. So the point is that if a semigroup S is simple, then you cannot quotient it by ideal, but you can still have homomorphic images from S to some others. So it could still have homomorphic images. So in some sense, it's not truly simple in that sense. That's why we have a different notion of truly simple semigroups. We must have this distinction here. Okay, and these are interesting objects. Truly simple semigroups are ones which cannot. So truly simple semigroups are semigroups which have no congruences at all. Okay, and they have interesting theory. For example, if a semigroup is truly simple, which means it has no further congruences that you can quotient by, they are actually simple groups. Okay, but we won't need this, so we're not talking about this further. We'll be dealing with simple semigroups. Right. Yeah. So first, let's look at an example. So this is our something which we have seen, this semigroup, left zero semigroup. So basically, everything in the semigroup is a left zero. okay, which means x times y will be equal to x for all x and y. So let's see what are the ideals of these things. Let's see. So if you pick an element y and you want to understand what's the ideal generated by that, okay, let's say you want to get an x from the y, then you just simply multiply it to the left and you get it. So certainly, I mean, even the left ideal is giving everything. So the ideal of every element is the whole thing, which means there are no proper ideals. So it is simple. Okay, it's more than that. So we can just look at. So we know what the left ideals are. We can look at the right ideals. The right ideals for, so if you pick an element x, right, if you pick an element, sorry, one second. So if you pick an element x and you multiply it to the right by anything, you're just going to get x. So the right ideals are only the elements. Okay. So this we are seeing an example where it's simple, but at the same time, the left ideals, there's only one left ideal, and the right ideals are all points. So all the right ideals are also incomparable, and the left ideals is just one, so that's also incomparable. So this is what is known as a completely simple semigroup, but we'll define it later. Right. So right. So what are J classes? So if you look at a J class, right, then every element generates the same ideal. So a J class will have no proper ideal, right? So simple semigroups are like J classes. Okay, are like in a finite case, they are like D classes. Okay, so every D class is is in some sense simple, though it might be null. So we'll see the conditions there. We have to give a group structure, semi-group structure on that, and then, but we can think of simple semi-groups like that. Okay? And that's the way in which we will use, because we'll be starting with a semi-group, and we'll have the D classes, and then we'll try to give it the structure of a completely simple semi-group. Then we'll use the structure theory of completely simple semi-groups there. So, but yeah, for the moment we can think of simple semi-groups as just a D class kind of. Right. So now we come to the next thing, that is completely simple semigroups. Okay. So this is a distinction that has to be made in the infinite case, which is what I was first going to also cover, but then this was already long enough, so I didn't go to the infinite problems of finding ranks and so on of infinite semigroups. Yeah, but still, so a completely simple semigroup. So it is a simple semigroup to start with, but at the same time, we are putting these desirable conditions of having minimal right and minimal left ideas. Okay, again, an example that we have seen, left zero semigroup. And in fact, obviously, any finite semigroup will also have minimal left and right ideas, because you can't have a infinitely decreasing chain. Okay, but at the same time, okay, so just a few comments. This is the right class of simple semigroups, because simple semigroups by themselves don't have this nice properties. We need this what is known in algebra as an Artinian condition, having a minimal like any chain must have a smallest and so on. Artinian conditions to make them behave. Yeah, and so we'll see that these completely simple semigroups, even when the semigroup is set theoretically infinite, completely simple semigroups can still behave like finite semigroups, meaning that we'll see that even if it's infinite, they are still just one D class and not one J class. And we'll also see that they are regular and so on. And so they have idempotents, and so they behave a lot like finite semigroups. A lot of properties of finite semigroups can be extended to infinite if we add this complete condition. Okay, so it's sort of desirable condition. Right. But sometimes your semigroup may have a zero, and when it has a zero, then you don't want to call